right, so looking at example number 5, you can see that it is completely condensed and we want to expand it. So I notice first things first, I've got the fraction bar. So the fraction bar has to be changed to subtraction. And I see that I have my radical. My radical is going to have to change to a rational exponent. So I'll have log base A of x squared plus 1, oops, sorry about that, to the 1/2 over my x cubed x plus 1 to the 4th. Okay, so first things first, let's go ahead and make that 1 look like a 1. That's ridiculous. Okay, so I'm going to have log base A of x squared plus 1 to the 1/2. Now here's my fraction bar. Since I have a fraction bar, when I expand it, I'm going to have to change division to subtraction. So I have log base A of whatever is down here in the denominator, which will be x to the 3rd times x plus 1 to the 4th. Okay, so notice that I took my division and changed it into subtraction. I took my radical and changed it to a rational exponent. So now, as far as this goes, I've got log base A of x squared plus 1 to the 1/2 minus. Now, as I look at the denominator, I see that there's a product in the denominator. So what I'm going to do is I'm going to put a large parenthesis, and I'm going to change my multiplication into addition, because everything has to be expanded. When it's completely expanded, there should be no multiplication, no division, and no exponents on the outside. Now, you might have some exponents on the inside of a parenthesis if it's part of an addition or a subtraction problem, and that's perfectly okay. But if you've got a multiplication problem like this, you've got to change it into addition. But since it's in the denominator, that minus sign is going to have to distribute to every part of this product. So I'm going to make this log base A of x cubed, and since this is my product part, I'll have plus log base A of x plus 1 to the 4th. Now, I'll have, once again, log base A of x squared plus 1 to the 1/2, and since I'm subtracting the denominator, which is a product, I'll have minus log base A of x cubed, and this plus right here becomes a minus log base A of x plus 1 to the 4th. Okay, so that'll trick you if you're not careful. Since I've made everything from division and multiplication into addition and subtraction, now I'm going to get rid of those exponents. So this exponent of 1/2 is going to come to the front as 1/2 log base A of x squared plus 1 minus, let's bring this third power to the front, 3 log base A of x, and bring this fourth power to the front, minus 4 log base A of x plus 1. Now, as I look at this, I see that I don't have any more multiplication, I have no more division, I have no more exponents on the outside. My eye is drawn to this exponent right here, but if you'll notice, this exponent is actually a part of an addition problem, so there's nothing that I can do to get rid of this exponent of 2. So this is now completely expanded, okay? This is my condensed form, what I started off with, because I have one logarithm and I have all multiplication, all division, all exponents. This is my completely expanded form, where I have no multiplication, no division, no exponents, except for this one that's part of an addition problem. So this is expanded. Notice each part has its own logarithm. This is condensed. One logarithm. I can have a radical, I can have exponents, I can have multiplication, I can have division. Okay? All right, now let's go the other way. Now let's look at some expanded form problems and let's condense them into one single logarithm. So here we have log base A of 7 plus 4 times log base A of 3. Now this is expanded because I've got addition, no exponents. And now I'm going to condense it to one logarithm, and I'm going to use exponents now. So since I have addition, I know that I can change that into multiplication. But remember, when we were going from condensed to expanded form, we moved the exponents at the end. When we're going from expanded to condensed, we're going to have to fix the exponents first. So I'm going to have to take this big 4 and change it to an exponent first. So log base a of 7 plus log base a of 3 to the 4th. So let's go ahead and pull that log base a, because when you condense, you're only going to have 1. And since we have addition, we're going to change this to multiplication. 7 times 3 to the 4th. Now, I know 3 to the 4th is 81, and then 81 times 7 is 567. So I have log base a of 567, and this is my condensed form. Okay, take a moment and write that down. All right, let's look at our next problem. Okay, I've got 2/3 times the natural log of 8 minus the natural log of 5 squared minus 1. My eye is automatically drawn to that subtraction. So I know I'm going to have division, but I've got a number in the front, so let's bring it to the top as an exponent. So go ahead and pull your natural log. Now, whatever you have in the front, that's going to be your numerator, 8 to the 2/3. Then whatever you have behind the subtraction problem is your denominator. So as I look at 8 to the 2/3, let's think about that for a moment. That denominator, 3, is the root of your radical. So what I have is the third root of 8. Well, it's 2 times 2 is 4, 4 times 2 is 8. The third root of 8 is 2. Now, whatever I have up here, this is going to be the exponent I'm going to put in my answer. 2 times 2 is 4. So now I have the natural log of 4 over 5 squared is 5 times 5, or 25, minus 1 is 24. So I have the natural log of 4/24. Well, being good math students, we're going to reduce 4/24. 4 into 4, 4 into 24. That gives me the natural log of 1/6. And that looks pretty condensed to me. But as I think about it, we learned a property earlier that said when we take the natural log or the log of 1, it equals 0. Okay, do y'all remember that property? I must have thrown those other papers away. But if you break this back apart into numerator and denominator, the natural log of 1, you can think of it this way. That's e to the y equals 1, so y equals 0, right? So the natural log of 1 is 0, and 0 minus the natural log of 6 is the negative natural log of 6. So we had to think outside the box on that one just a little bit, okay? So anytime you have natural log of 1 or the log of 1, it equals 0. All right, kiddos, now look at C. Wow, what a problem. We've got log base A all the way through. We got plus, plus, we know that's times, isn't it? And we have minus, which we know is divide. So let's go ahead and look and see if we have any big numbers in the front. We have no big numbers in the front, so no exponents that we need to fix. Go ahead and pull the log base A. Now, we're going to take each part of this addition, and we're going to multiply it together in our numerator. So we'll have x times 9, well, I know that's 9x, times x squared plus 1. Now, in my denominator, which will be behind the minus sign, I just got a good old 5. Well, I'm looking at this, and I'm not really seeing anything else I can do with it. I could distribute 9x times x squared and 9x times 1, but I don't have to. This is a pretty good answer, okay? So this is my expanded form. Notice I had a log for every part. This is my condensed form. I have one log, okay? Anytime you see that minus sign, you've got to have that fraction bar there. What's behind it is in the denominator. What's before it is in the numerator, okay? Expanded form, condensed form. Okay, making good progress. Now, let's look at some no-nos, some things that we will not do, okay? One thing that we're going to have to understand is if you have log base A of mn, That's a product, isn't it? So we can change that into log base A of m plus log base A of n. This is the property. But a lot of times, students will get it a little mixed up, and they want to take an addition problem and change it into log base A of m plus log base A of n, kind of like distributing. You cannot do that. It's 1 log with multiplication, 2 logs with addition. You can't take 1 log with addition and change it to 2 logs with addition. It's 1 multiplication, 2 addition. We don't distribute here is what I'm trying to say. So this is a huge no. Don't do it. Now, another no-no that students often do is taking Now, this is expanded form. When we condense it, we pull the log, right? And then we put m over n. So this is the property. Do not do log base A of m over log base A of n, okay? When you go from expanded form to condensed form, there's only 1 log, not a log for each part of the division problem. And then finally, when you have a quotient, okay, if you have, or not a quotient, I'm sorry, an exponent. Okay, if you have this, you've got your log base A of m, and the whole thing is raised to the r. You do not do this, okay? It has to be log base A of m to the r. There should be no parenthesis, and then you can bring it to the front. Okay, so if there's a parenthesis where the logarithm is raised to the power, you cannot bring it to the front. If there's no parenthesis, you bring it to the front. So there's a distinct difference there, so be very careful. All right, kiddos, our next property, if the log base A of m is equal to log base A of n, then m is equal to n. We have seen this before. Log base A of x plus 9 equals log base A of 6. See how both of these are log base A? So you can actually drop the log base A and solve for x. Okay. And finally, let's talk about the change of base formula. If you have log base A of m, what you can do with the change of base formula is change it into a log base 10. You can take the log of m and put it over the log of A. And that'll be a log base 10. And also know you can use a natural log and get the exact same result. So if we have the problem, let's say log base 5 of 89, okay, we know that we can do MAM on our calculator, math, alpha, math, and we can get the answer. But back in the day when we couldn't get the answer, we had to use change of base, and we change it to log base 10. So we take the log of 89 and put it over the log of our little number here, which is 5. And you can also do a natural log and get the exact same result, okay? So as I look for my calculator, here it is. Okay, let's turn this on. Oops, I need batteries. Okay, so if we do MAM, math, alpha, math, remember we can do log of any base. So we can do log base 5 of 89. Okay, everybody see that? And this is my result, 2.7889. Now, if we do change of base, okay, we can do the log of the big number. So log of 89 over the log of the little number, which will be log of 5. Okay, everybody see that? Looky there, same result. And if we do alpha y equals again, let's do that. Okay, so we'll do natural log. So do natural log of the big number, 89, over natural log of the little number, 5. Okay, does everybody see that? So we got this one right here from MAM, Math Alpha Math, and we can do log of any base. Okay, this is my change of base formula using log base 10, the log of the big number over the log of the little number. And then this is the change of base formula using natural log, the natural log of the big number over the natural log of the little number. Okay, but you'll see in all three cases, the results are the same. Okay, you get the exact same answer, 2.7889. So the whole point of this is, you're probably thinking, well, I don't need the change of base formula because I can do this in my calculator, which is true. But you also need to know that you can change any base into a log base 10 and a natural log, and you'll get the same result. Okay, so complete your assignment. If you have any questions, shoot me an email and I'll try to answer them in a timely manner. Y'all have a good day.